Hello everyone and welcome to the second episode of the Boise High School Rocket Club rocketry course. Today we're going to be talking about some of the nitty-gritty stuff now, nozzle theory. In this section we will once again have some prerequisite knowledge that you need to know, namely in chemistry, as this section will be pretty intensive on the use of thermochemistry in its relation to the ideal gas law, enthalpy, entropy, thermochemistry, specific heat ratios, etc., etc. And then also, of course, just some general understanding of physics, which includes just, forces, momentum, etc., and especially energy and its conservation, obviously. And then for math, it's actually pretty light, this one. Pretty much just algebra, and you should be good. Okay, so for starters, our rocket nozzles are going to be dealing with compressible gases moving through them, really hot gases specifically. And so in that case, we need to understand some of the basics of compressible fluid flow. The first thing that you need to know is that mass is always conserved throughout the entire fluid flow. This means that the mass coming in is the same as the mass going out, or the mass flow rate is equal along the entire fluid flow. If you were just suddenly getting mass out of nowhere, or losing mass out of nowhere, that would kind of violate the laws of thermodynamics, and so it doesn't happen. We can represent this mass flow rate as being equal to the density of the fluid times the cross-sectional area which it's traveling through times the velocity at which it's going. Secondly, the fluid flow will mostly be isentropic, which basically means that there's no change in entropy from one side of the fluid flow to the next. It stays basically the same the entire time. And so the entire process is reversible. You can condense the fluid flow down into a small area, blow it up into a big area, condense it down, blow it up, and the properties of the entire fluid flow will inherently stay the same and completely reversible. Thirdly, we're going to assume that our fluid flow is basically adiabatic, which means that all of the heat within the fluid flow system will stay the same. There's no heat transferred in or out. Now, of course, this isn't entirely true, as there will be some heat exchange with the walls of the nozzle. However, for the purposes of these calculations, it's actually a pretty accurate assumption. Next, in a compressible fluid flow, the rate at which a pressure wave can propagate throughout the fluid flow is known as the speed of sound, which is represented with this equation, where K is the ratio of the specific heat of the gas at constant pressure over the specific heat of the gas at constant volume, and R is the universal gas constant, R prime, over the molecular mass. T is simply just the temperature in Kelvin. The Mach number m can then just be written as the ratio of the velocity of the flow, v, over the local speed of sound. The ideal gas law can then also be written as such. This is just a modification of the original ideal gas law. V here represents the specific volume, which is just 1 over the density rho. Now with all of these assumptions and equations in place, we can now use the isentropic flow relation equations, as shown here, to make some derivations. Since the total energy of the fluid flow is going to be conserved, the energy per kilogram of the entire flow can be written as the sum of the fluid kinetic energy plus the fluid temperature energy. And since these are going to be equal at any one point 1 and 2, you can write them as equal. You can also write this as a difference in enthalpy between the 2 points to do the exact same thing. Either way works. Also, to note in this equation, there's a constant J put in there that's just used as a conversion between imperial and metric units. Since we're using metric units, that constant is just going to be 1, and so will be negligible in this entire equation. If the fluid flow were decelerated to a stop, then all of the fluid kinetic energy would be equal to 0, as the fluid is no longer moving. This means that all of the energy would then be put in the form of heat energy. This point is known as the stagnation temperature, the temperature at stagnation, when the fluid is not moving. Using either the energy or the enthalpy equations, we can set Vy equal to 0 and Ty equal to the temperature of stagnation. Thus, we can solve for this stagnation temperature as a function of the temperature and velocity at another point. By solving for V in the Mach number equation and then plugging into the stagnation temperature equation, we get stagnation temperature as a function of Mach number. Using this equation, plugging into the isentropic flow relation equations, and then solving for pressure instead, we can get stagnation pressure. Now hold on a second. Let's take a step back and look at what we're really doing right now. What do these equations mean? What are they actually telling us? Let's start with the equation on the right. If we divide everything over except the t, then we can notice that as the Mach number increases, or as the velocity of the flow increases, the temperature decreases. This is because of the conservation of energy as outlined earlier. Since the total energy of the system must stay the same, as the fluid kinetic energy, or the speed, increases, then to compensate and keep energy the same, all of that energy must come from the heat energy. And so, as kinetic energy increases, temperature energy decreases, and so the temperature goes down. Next, we have one more relation, the key to why nozzles are shaped the way they are. Now, sadly, I won't derive this in this video, however, I will give some links to derivations elsewhere. This is called the area-velocity relation. Now, for subsonic flow velocity with Mach numbers less than 1, this equation has the gas behave like you would expect. Since the right side of the equation is negative, as the cross-sectional area of the flow decreases, the velocity must then increase, and vice versa. This keeps the left side of the equation negative as well. So for subsonic velocities, the gas behaves just like water in a hose. If you decrease the area, by putting your finger on top of the hose, then it increases the flow velocity. What happens, however, if the Mach number is greater than 1, aka the flow is supersonic? Well, in this case, the equation is going to be positive on the right. And so in that case, if you increase throw area, you increase velocity. This is exactly why rocket nozzles are shaped the way that they are. Since their job is to take high pressure, high temperature, low velocity flow and convert it into low pressure, low temperature, high velocity flow, the best way to design your nozzle is to have it converge down while the flow is subsonic until eventually it hits sonic speed, Mach 1, at the throat, and then blow it up into a larger area to increase it further to supersonic speeds. So now let's start doing some derivations for the properties of this flow. I'll use this diagram as a reference for all of the points in our rocket nozzle, point 1 being within the chamber, point T being the throat, and point 2 being the exit plane of the nozzle, and then point 3 just being the atmosphere. By plugging points 1 and 2 into this equation, and then solving for V2, we can find what our exhaust velocity will be. By rearranging parts of the isentropic relations and the enthalpy equations, and then solving for the entire thing in terms of just T1 and the pressures P2 and P1, then we get this equation for V2. Now, so long as the chamber port area to the throat area ratio is greater than 3, then the velocity of the fluid within the chamber is basically negligible, and we can pretty much assume stagnation conditions. Thus, V1 can be set to 0. This gives our final full equation for the exhaust velocity V2, which has some interesting things we can begin to notice. First off, we can see that by increasing the ratio between the chamber pressure and the exit pressure, you can increase the exhaust velocity. Secondly, we can see that by increasing the combustion temperature within the chamber, we can increase the velocity. And finally, we can see that by decreasing the molecular mass of the propellant, we can increase the exhaust velocity. This means that propellants with lower molecular masses, like hydrogen, the element with the lowest molecular mass, will be the best propellant. To get our mass flow rate, we need to be able to find the conditions at the throat of the nozzle. By simply taking these equations and setting the Mach number equal to 1, we find the conditions at the throat of the nozzle. This pressure ratio right here is very important and is known as the critical pressure ratio. This ratio is a function purely of the chemical propellant properties. Basically, as you take the gas flowing out of your chamber and you condense it down by decreasing the area, as soon as it reaches a certain critical throat area, then it'll reach Mach 1 and therefore have this pressure ratio. And this pressure ratio will stay fixed unless you increase or decrease the chamber pressure. The reason this ratio is important is because as soon as it is reached, the chamber is essentially cut off from the rest of the world. Well, why is that? The reason is because the gas is moving at Mach 1 through the throat and going downstream. And so, if there's any changes to the pressure downstream, that information cannot travel upstream because it can't travel faster than the speed of sound. And the gas is already moving at the speed of sound. And so, only changes in the chamber itself can cause any changes to the velocity of the fluid. Since we know the fluid is moving at the speed of sound at this point, we can take our equation for the local speed of sound and simply plug in the formulas we have here Once this critical pressure ratio is reached, then both the density and velocity become fixed at this point in the nozzle. This thereby fixes the entire mass flow rate across the entire thing, and the mass flow rate reaches its maximum value. This is called choking the flow. By substituting rho for this specific volume, we can use some of our other equations that we derived before to then get the mass flow rate. That gives this equation, which you can see shows a direct linear relationship between the throat area and the chamber pressure and the mass flow rate. By doing the same thing for another point in the nozzle, you can also obtain the mass flow rate, and by dividing these two things, you can get the area ratio between some other point and the throat. Finally, we can write our original thrust equation in terms of these formulas, which gives this. From this equation, we can see a couple of things. The first thing being that the thrust is directly proportional to both the area of the throat and the chamber pressure. It also has a direct linear relationship with the pressure difference between the exit plane of the nozzle and the surrounding atmosphere, as well as a direct relationship with the area of this exit plane. This function is at its maximum when the pressure difference P2 minus P3 is equal to 0, aka when the pressure of the exit plane of the nozzle is equal to the pressure of the surrounding atmosphere. We can understand why by looking at this visual. Gas will always tend to expand or contract until all of the pressures are in equilibrium, in this case when the pressure of the gas is equal to the pressure of the surrounding atmosphere. Thus, in the case of an underexpanded nozzle, where the pressure coming out of the nozzle is greater than that of the surrounding atmosphere, you could have just simply expanded the nozzle a little bit bigger so that you could have decreased the pressure and temperature within your nozzle and therefore gotten more velocity and therefore more thrust. Overexpansion, on the other hand, is when the pressure coming out of the nozzle is less than the surrounding atmosphere. In this case, the pressure difference is going to be negative, thereby decreasing your thrust. Thus, a nozzle is called optimal when the pressure coming out of the nozzle is equal to the pressure of the surrounding atmosphere, as the thrust is maximized. Sometimes we'll be forced into scenarios where we have to choose between underexpansion and overexpansion. In general, underexpansion is always better than overexpansion. This is just because in underexpansion, you could be getting more thrust, whereas with overexpansion, you are getting less thrust. Alright, so let's do an example problem using some of the formulas we've talked about. So suppose we have a rocket engine at sea level with an atmosphere pressure of 0.101 megapascals. That's just the atmospheric pressure at sea level. It has a specific heat ratio of 1.3 within the exhaust gases, a chamber temperature of 2800 Kelvin, a chamber pressure of 200 bar, a molecular mass of the propellant of 17.5 grams per mole, and then a mass flow rate of 500 kilograms per second. Let's get the thrust, the pressure and velocity at the throat, the exhaust velocity, the specific impulse, as well as the diameter of the throat and exit. Starting off with the low-hanging fruit, the throat pressure, we simply just take this equation right here, the pressure ratio, and multiply both sides by the chamber pressure, P1. Before we plug into this equation, however, we need to remember that we want our pressure in the metric unit pascals. Therefore, we have to remember that 1 bar is equal to 100,000 pascals. So our 200 bar chamber pressure needs to be converted into 200 million pascals. Plugging into our equation then, we get 109 million pascals, or about 1.09 megapascals for our throat pressure. As you can see, the throat pressure is a lot less than the chamber pressure. The throat velocity may also be readily obtained, just by remembering that R is equal to the gas constant R prime divided by the molecular mass. This gives a throat velocity of 1226 meters per second. Now for calculating the exhaust velocity V2, we need to remember that we are designing an optimally expanded nozzle. Thus, our exit pressure, P2, is going to be equal to the ambient atmospheric pressure, 0.101 megapascals, or 101 million pascals. So we get an exhaust velocity of 2850.8 meters per second. Now we can use this equation to get our thrust, and since P2 was set equal to P3, the pressure term is equal to 0, and we just have to multiply our exhaust velocity by our mass flow rate. This gives our rocket a thrust of over 1.4 million newtons. By dividing our thrust force by the mass flow rate times the gravitational acceleration, we get a specific impulse of 290 seconds, which is pretty good. To get the throat diameter, we first have to get the throat area. We get the throat area by dividing the mass flow rate by basically everything that isn't the throat area on the right side of the equation. This gives a throat area of about 0.04 meters squared, or 432 centimeters squared. Since the cross-sectional area of our throat is basically just going to be a circle, we can set this area that we found equal to the equation pi r squared, the area of the circle. By solving for the radius and then multiplying the radius by 2, we then get a throat diameter of about 23 centimeters. Now by taking this equation and setting the point y to just be the point 2 at the exit, we can divide AT by everything on the right side to get the area of the exit. Thus we get an exit area of 6,817 centimeters squared. Using pi r squared again and solving for the diameter, we get an exit diameter of 93 centimeters, or almost 1 meter. What if we were to fire this engine until our rocket reached an altitude of 20 kilometers, where the atmospheric pressure drops to 0.00547 megapascals? Well, in this case, our nozzle will become underexpanded, as its exit pressure of 0.101 megapascals is greater than the current atmospheric pressure. How does this change performance? Now we need to take the original thrust that we got and add on the pressure term, also making sure to use the value for A2 that we calculated previously. Calculating it out, we find that our thrust increased from 1.425 millinewtons to 1.49 millinewtons. Our specific impulse also increased from 290 seconds to 304 seconds. What if we were to instead optimize our nozzle for this height? Well, we find that the newly optimized nozzle will have a larger exit diameter and will therefore give a higher thrust and specific impulse than the sea level nozzle performing at the same altitude. So we can draw two conclusions. One, at higher altitudes, rocket engines perform better, as the pressure of the atmosphere decreases, and so the pressure term of the thrust equation will increase. Secondly, a nozzle optimized for a specific altitude will always outperform a nozzle not specified for it. This is, for instance, why SpaceX's Raptor vacuum engine has a larger bell diameter than that of their sea level one, as it is optimized for the higher altitudes and lower pressures. Alright, and that concludes this section of the course on nozzle theory. Tune in next time where we'll begin talking about real nozzle performance as well as solid propellants.